Alright. We're going to try a little video with discrete math here for you. Okay, so a couple things, and I got this also, trying to post this as notes as well, so you should be able to access everything I write as well as listen to me do this little deal. Couple things before I get too far into this. Let's understand, all right, for this class, basically, what we would normally be doing is going into calculus. I'd be talking about the limits, but I think I'm in a, so essentially this is bonus math. We'll save the limits for when we get into calculus. That's going to be better with us in the classroom together, and so that's what we're shooting for. So I have done this in the past with pre-calculus classes, but and so again, I want to kind of just throw this out and see where we can go with it. Basically, this is basic combinatorics. It's how numbers kind of work together. And if you were in stats or probability, I'm hoping you saw some of this, but we'll see. So the basic thing I want to start you off with is what's called the counting principle. Okay, and the counting principle is essentially going to talk to you about how many different ways can you arrange certain objects. So essentially, hey, okay, I've got an up arrow, a left arrow, and a down arrow. How many different ways or how many different arrangements could I put those things together? Well, obviously there's one. You know, I could switch those two. There's a second one. I could, let's see, switch the two outside ones. I could go down, left, and up. Let's see, I could switch the two ending ones so that I could go up, down, right. Okay. And obviously, if this is only 3 objects, if I had well more than 3 objects, this is going to take a long time. And the one way you could think about it, or that I want you to think about it, is, all right, we're essentially filling 3 different locations here. And in each location, we're putting one of these symbols. Well, the counting principle says, fine, how many choices do you have for that first option? Well, you have 1, 2, 3 choices. So if we were to start filling that in, we have 3 options multiplied by, well, you took one, you picked one and dropped it in there. Now you have 2 options left. So say I put the up arrow in, so it's sitting in this. That means the next option I could either go with the left arrow or the down arrow. I have 2 options for right there, which means here I've got 1 option. So I'm looking at 3 times 2 times 1. There are 6 options. Now I drew 4 of them. That means that I should be able to find 2 additional ones. Let's see, I'm thinking I've got another one that's got a down arrow first, so I could draw them out. I could go down arrow, up arrow, left. And let's see, I think I've got another one that goes left arrow, down arrow, up arrow, and there's all 6. Now obviously if I have way more than 3 objects, then this would get pretty extensive pretty quickly. Okay? But that's known as the counting principle. You can do that with any number of objects. Now if you wanted to think about telephone numbers, okay? So telephone numbers, how many different telephone numbers? And we understand that telephone numbers are 3 digits followed by 4 digits. And often they put a disclaimer and they're like, hey, this first digit here can't be a 0. And so we could count out the number of possibilities by simply using the counting principle. We have 10 numbers, 0 through 9, that we can work, except on this one, we have 9. Okay, there are 9 options. 1 through 9. But now, here we've got 10 options. Okay? Because we allow for repeats, and that's different from what's going on up here. Here we didn't allow for repeats. They couldn't go up arrow, up arrow, up arrow. And if that was the case, then I would be 3 times 3 times 3, or 27 different options that could come out of those. But here, we allow repeats, so, you know, we could pick 10 different digits. And then for this, you still have 10 different digits. And for this next number, and I don't want you to consider that as a minus, that was the dash in the phone number, but you have 10 digits left for each of those options. And so if we looked at, all right, how many phone numbers can I make? Basically, I've got, what, 900, 9,000, 90,000, 900,000, 9 million. Okay. There are 9 million phone numbers that I could create, and then that's where we then have to add the idea of an area code. Essentially, each area code can handle up to 9 million phone numbers. And that's where you can look at, well, okay, Montana, we've got the 406 area code. We didn't need another area code in this state because we can cover up to 9 million unique phone numbers based off of the counting principle. Another way to envision the counting principle is through the use of tree diagrams. So, you know, essentially you could look at, hey, how many different combinations of sandwiches we could make if we could do wheat, white, ham, turkey, beef, and then we could say, let's just essentially stop it there. So if we start doing a tree, well, based off your tree, you could go wheat or white, and then off of white, you could go the ham, turkey, beef, and white, you could go the ham, turkey, beef, and when you get done with this all, you're looking at, oh, well, there's 6 total sandwiches. We could do white beef, white turkey, white ham, this was wheat, and we could do white with ham, turkey, and beef, okay? So that's another way, and it also illustrates the counting principle, that you had 2 options multiplied by 3 options, you have 6 total sandwiches that you could put together, okay? Brings us to the idea of a permutation. Okay? A permutation is basically the number of ways we can arrange n objects. Okay? So if I had 21 of you in class, how many different combinations could I make? And I have 21 desks, and each of you sit in a desk, so how many different unique combinations? Well, if we went through this and said, hey, I could do 21 on the first desk, 20 on the second desk, 19, 18, 17, all the way down 3, 2, 1, and that's covering all the numbers. Okay, so on that first desk, I've got 21 options. The second desk, now I've got 20 options because somebody's sitting in the first desk. 19 options. If I were to figure that out, then I've created, and this is counting principle, but this is also 21 factorial. So there's a shorthand way to write that. And this explanation or exclamation point is interpreted as a factorial. A factorial just says, hey, take 21 and multiply it by all the numbers down from that regard. And if I was to go to my graphing calculator here, let's see here. Gotta go to my calculator. Okay. I can do factorials on the calculator. Sorry. No, I don't want to cancel that. So see, this is just like in class where the calculator never works right. Okay. And I want to continue with the trial version. Okay. And we're looking for that factorial key. And we'll need this for a few other things to talk to run you through as well. Okay, so the factorial key comes under math and number. Oh, sorry, let's go over to PRB. So under on this particular calculator, math and PRB, you can see here's that exclamation point, and actually the other two we need are NPR and NCR that we'll need to deal with this. So if I wanted to do a number and say, hey, I want to do 21 math, go over to probability, and I'm going to go down to option 4, 21 factorial, how that's read. Okay, now that's a lot. That is a 5, and then I'm going to basically move that decimal point over 19 different places, so that number's very big. Okay, so if there's 21 people to arrange in 21 desks, I have basically that many combinations, which I don't even want to go into what number that is. I mean, it's beyond trillions, right? It's beyond zillions or whatever. Okay, but so that's the concept of our factorial. So, now what we can change on this is we want to talk about distinguishable permutations. And the best way to explain a distinguishable permutation is to say, let's take this word, that. Very simple word. How many different ways can we rearrange these letters? Well, distinguishable means that we don't want to count things that look the same more than once, which that means if I was to switch those two T's, they look the same, and that is not distinguishable. Okay, so if it doesn't change, so well, we have 4 objects. So if we thought about how many different ways can we do that, well, we could do 4 factorial. But the problem now is, and that would be 4 times 3 times 2 times 1, which is 24. But the problem is we would have to eliminate the ones that repeat. So the one that has this TT, where it just flip-flops, that's going to be removed. So a distinguishable permutation, we must remove repeats. Okay, so we're looking to remove the things that repeat themselves. Well, the way we do that is we divide out, and we're going to take each letter. So let's take T. How many times does T appear? Well, twice. So we're going to divide that out by 2 factorial times, how many times does H appear? Only once, so 1 factorial. How many times does A exist? Once, 1 factorial. So now we're looking at 24, because that's 4 factorial. 4 times 3 times 2 times 1, if you want to write it out longhand. 2 factorial is 2 times 1. 1 factorial is 1, and 1 factorial is 1. And you could do something like this. Well, that 1 cancels, that 2 cancels. And ultimately, you end up with 4 times 3 over 1. There are 12 distinguishable permutations. Okay? If we take other words, let's take just the word the. Okay? Well, how many different ways? Well, there's 3 different terms, so there's your 3 factorial. Now, this is just a regular permutation because there's no letters to repeat, but just to show you that the distinguishable permutation format works, T appears once, H appears once, E appears once, and you end up with 3 factorial over 1, or just 3 factorial, 6. Okay? Well, let's take the word Montana. Okay? How many different permutations of the word Montana can we create? Well, we can count up. We've got 7 letters. Is that right? Yep, 7 letters. So that's going to be 7 total letters. That's going to be 7 factorial. And we can just run. All right, M. M only appears 1 time. Okay, divided by 1 factorial. O. O only appears 1 time. 1 factorial. Okay. N. N is twice. Okay, 2 factorial. T. 1 time. 1 factorial. A. All right, that's twice, so 2 factorial. Now notice, we've already dealt with the N, we've already dealt with the A, so the number of distinguishable permutations is going to be 7 factorial divided by all of that. So let's go to our calculator here. Right? So we're going to go 7 math 7 factorial divided by, well, how about we could go to this. 2 factorials 2 times 1 and 2 factorials 2 times 1 times all the ones. It's going to be 4. Okay? So that is 7 factorial over 4. So let's just take this number, divided it out by 4. So there's 1,260 distinguishable ways that we could arrange the letters of Montana. Right? And distinguishable again means that, hey, they look different. They are not the same. You know, so if I just switch these A's, they look the same. Okay? Now this changes quite a bit if I was to do this. M in blue, O in black, N in orange, T in yellow, this A in that funny color, this N in that color, which is different, and that A, which, well, let's see, we'll go copper so that it looks different. Okay, so now these are not distinguishable, or they are distinguishable because all the letters are different colors, and so this A and this A are not the same. This N and this N are not the same. This would turn into 7 factorial, or there's now 5,040 different ways I can arrange that, because I can't divide out anything because the letters are different. You can tell the difference whether I put the copper A first or the blue night A in first. Okay, so all right, let's talk permutation counting formula. This is the NPR, which has a mathematical formula to it of n factorial over n minus r factorial. This is how you would do it by hand. Here's what this is used for. Okay, this would be the situation, all right, 10 people are running for offices. There are president, vice president, secretary. Top vote getter's the president, second vote getter's vice, third vote getter's secretary. So it matters what order you finish in. So this is the thing that says, hey, order matters. The placement or the distinguishable, it matters where you get placed. Okay? So if I had 10 people and I get to properly place in the select order 3 of you, I would be calculating 10P3. Okay? So 10P3 says out of a group of 10, I'm going to place 3 of you in a specific location. Okay? And so longhand, this turns into 10 factorial over 10 minus 3 factorial, or 10 factorial over 7 factorial. Okay? And we can do this by hand, or we could also do it by calculator in a minute, but by hand this looks like 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1, cancel, cancel, and I'm looking at 720. There are 720 different outcomes that I could expect. Now in probability then we would say, hey, what's the probability of person A actually winning the president? So we would calculate how many of those 720 have A as the top vote getter, and then turn that into a fraction, and that probability would be the percent chance that that person has to win. Right now we're basically just calculating what's a full sample size. Okay, on a calculator, let's look at this 10P3. On our calculator, we have a key for that. We're going to hit the 10 first, and then we're going to go to math, and under probability, you'll see it show up right there, option 2, NPR. Okay, and so it'll put it, 10 is the N, and the R is the 3, and there's our 720. So again, that's under math and PRB. And now when I go there, the other one you're going to see is NCR. So NCR might be used in this case. So those same 10 people, the top 3 vote getters win. I don't care the order. They all hold the same office. They're all representatives. So that's going to be the NCR option. So that's 10 CR, and let me throw that formula out at you. So NCR is equal to n factorial over r factorial n minus r factorial. Okay, oops, I don't have that so you can see it. So there's my NCR, n factorial, or r factorial, n minus r factorial. You see, you're dividing out more things, and that's going to reduce this number because now order doesn't matter. So ABC winning and CBA winning are the same thing. Okay, so order doesn't matter. So we would expect a lesser number than 720 if we were going to do 10C3. So let's go to my calculator here for a minute, clear this off. I want to go 10 math probability option 3, choose 3. And there's only 120 unique combinations, so those 10 people working for office in that case are dropping down to 120. So NCR is when our order doesn't matter, NPR, the order that you finish in, absolutely matters. Okay, so I just want to run through some samples of these questions. I know I gave you evens, so I'm going to start off with some of the odds. Like I'll start off with number 1. So number 1 says count the number of ways that each procedure can be done. Line up 3 friends for a photograph. Okay, well, again, I have 3 options for the first location, which gives me 2 for that and 1 for that. I've got 6 total options that I could line them up. So there's your answer for 1. And honestly, if you just wanted to go 3 factorial equals 6, that's good. I just use that little chart to help you visualize, hey, here's what's going on. Okay, moving on, let's look at number 3. Arrange 5 books from left to right on a bookshelf. Okay, so, all right, you have, boom, I'm going right there, 5 factorial. Okay, and I'm going to go right on my, no, I'm not, I'm just going to go 5 times 4 times 3 times 2 times 1. 20 times 3 is 6. 20 times 3 is 60 times 2. There's 120 different ways that I could go about doing that. Okay? All right, let's see, where do I want to go? Let's see. Well, we can go to number 9. How many distinguishable 11-letter words can be formed using the letters in Mississippi? So looking down here at number 9, MISSISSIPPI. Okay, they want to know how many distinguishable or different events can I build from Mississippi. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial is the total. So I'm going to fill 11 slots with a letter. Okay, count the M's. All right, there's only one M, so that's 1 factorial. I's, well, it looks like I got 4. 4 factorial. S's, I've got 4. 4 factorial. I already counted I's, I already counted S's. P's, I've got 2. 2 factorial. So I'm looking at 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. So let's go to the calculator. So let's go with 11 math factorial divided by, let's go quantity, 4 math factorial times 4 math probability option 4 for factorial times 2 math probability option 4 for factorial. Close that off. Okay, and so still within that, there's 34,650 unique ways that I can arrange the letters of Mississippi, okay, and have them work out. Okay. All right, let's see. Well, then I'm looking at, hey, here's like 15. 15's really simple. Hey, would you calculate 6p2? Okay, well, 6p2, I mean, if you want, you can go right to the formula, which is n factorial. Okay, so that's 6 factorial over 6 minus 2 factorial. And you might see that's 6 factorial over 4 factorial. And one thing you can see, 4 factorial means everything from 4 down in the numerator is going to cancel. Oh, that's 6 times 5, 30. So there is a way to do it by hand. And I just want that to be made aware to you. And again, you can do it on your calculator. Lots of different calculators can handle that. All right, now when you start hitting 19 to 22, they're talking about tell whether the permutation ordered or combinations unordered are being described. So like number 19 says, 13 cards are selected from a deck of 52 to form a bridge hand. Okay, well, the order that you pick them doesn't matter. It's not a specific bridge hand. Okay. So, well, or does it matter? Because every bridge hand might be unique, so that is probably a permutation. So if we're looking at 19, out of those 52 cards, permutation of 13 cards, but I'm not sure that the order that I pull them out of the pile matters. Okay, and I don't know anything about bridge. That might be the bigger problem. I mean, like if the first card's a 2, so I don't think that really does matter. I think we're looking at 52 cards. How many different ways can I choose 13? Because it doesn't matter the order. Think about it in terms of poker. All right, if you get 5 cards dealt with you, and the first card's a king, and the next card's a 2, and the next card's a 3, and the next card's a 4, and the last card's a king, well, that's still a pair of kings. You're going to take them in your hand, arrange them, and you're going to have king, king, 2, 3, 4. And the order that they were delivered to you doesn't matter. Somebody doesn't beat you and say, ha, I got 2 kings, but mine came on the first 2 draws. Might beat your 2 kings because you got yours on the first and the last draw. So those are going to be combinations. Those are the things you have to think about. Does it matter if the order is important, or can I do this without taking into account the order? Okay, let's look at 23. 23 talks about license plates. How many different license plates begin with 2 digits, followed by 2 letters, and then 3 digits if no letters and digits are repeated? So if I was going to do that, it said, all right, digits. So we were 2 digits, followed by 2 letters. So these are letters, followed by 3 digits. And they said no repeat. All right, well, fair enough. And I'm going to say that's no repeat anywhere. So if I go for my first number choice here, I have 10 different options. I can go 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And nowhere does it tell me that I'm seeing that I can't start it with a 0. So, so we're going to say I have 10 options for those first 2 digits. Now moving forward, I can't repeat. So since I can't repeat, whatever digit ends up here doesn't go here, so now I have 9. Okay? I think there's 26 letters in the alphabet, right? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and yeah, we'll go 26. Okay? So for letters, we're going to go 26, but we can't repeat. So now we're at 25. Now we're back to digits, but I'm going to say that we still can't repeat. So I only have 8 options left because I can't repeat these. So now I have 8 options, and then 7 options, and then 6 options. And this is a counting principle. We basically just counted up the number of options we had for each thing, and then if we wanted to find the totals, boom, 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 we're going to multiply those all together. Okay, and that's going to be a really large number. Also, let's see here. We're going to go 10 times 9 times 26 times 25 times 8 times 7 times 6. So we're looking at 19,656,000. So 19,656,000. So we're looking at 19,656,000 plates that it could be built in that manner. Okay? Let's see. 27, forming committees. A 3-woman committee is to be elected from a 25-member sorority. How many different committees could be elected? Well, okay, if I look at that, it doesn't matter. If you're elected, you're on the committee, you all have the same power. That means order doesn't matter. 25, choose 3. Okay? And again, go to the calculator to deal with these. 25, math, probability, option 3, 25, choose 3, 2,300 different, so there are 2,300 different committees that I could get formed. Okay, let's see here. Just looking through here. If there's anything else. No, I think that's enough to get you started. Okay, so again, we're looking at page 633 to 34. I think I went 2 to 42 evens. Okay, so counting principle, let's make this due next Tuesday. Okay, all right, thanks for watching.